Hello my dear you all, I am Rakesh Sharve from Sunbeam Sun City. My dear, today's topic is we are going for uses of dimensions. I will go for uses of dimensions after this quantity to discuss. These are the some physical quantity. In my previous video I have not loaded these physical quantities dimension, but you all know that as I told you that you have to do it from NCERT book. In the books you will find these dimensions also. So here the quantities are, the first quantity I have written stress, the second is strain. I will read the quantity. The first is stress, second is strain, and then here I have written the third quantity is elasticity constant. My dear, elasticity constant denoted by small e, but under that there are three quantity. One is called Young's modulus of elasticity, bulk modulus of elasticity, and shear moduli of elasticity, or you can say moduli of rigidity. Young's spelling is Y, starting with Y. It is represented as capital Y. Bulk modulus of elasticity is have some different abbreviation, that is denoted by capital K, where capital K, and shear moduli of elasticity or moduli of rigidity is denoted by eta. Eta is also a denotion of coefficient of viscosity. So we can't help in that sense, because sometime in physics two symbol is used for same symbol is used for different physical quantity. So here eta I have used for moduli of rigidity or shear moduli of elasticity, but the same eta abbreviation is used for coefficient of viscosity also, which is a property of liquid. Elasticity is also a property, my dear, but it is not only a property of liquid, it is a property of solid, liquid and gas all. Because elasticity you will observe in all the three states of matter. I will go to that. The fourth quantity is gravitational potential. My dear, in previous video I have told about electric potential. Now we will see what is gravitational potential and what will be its dimension. And the next topic, the last topic from my side, is moment of inertia. My dear, moment of inertia denoted by capital I. So these are the topics which we will discuss today. So let's start first with stress. What is stress? How will we find the dimension of stress? So now let's begin with the first dimension, that is a dimension of stress. So here I am writing stress. My dear, this term stress is actually, you must be knowing that somewhere, suppose we are saying, most of the students saying, sir, I have a lot of stress. This is in day-to-day life, we are using this word. Sir, I have a lot of stress. Studies, this is studies, that studies, this paper, this, that paper, physics giving me a stress. This question of physics is giving me a lot of stress. So my dear, what is a stress? Try to understand. Stress is nothing but it is defined as a force act on per unit area of our body. Am I clear? When I tell you, the force is actually called tension. I will tell you the force ka dusra naam is tension. I have told in my one of the video also, but today let me tell you this. Today we have written this formula, force by area. Na? You take this force as a tension. My dear, when we get the tension, right, by some work, so that tension will start acting on every area of our body. First we take tension, we collect tensions, right? Tension is not stress. Let me tell you one thing carefully. Tension is not stress. But what is a stress? That, sir, we take a lot of tension, that is nothing but force. And that tension will be start acting on per area of our own body, because this word is a word related to term elasticity. My dear, let me tell you, this stress is a word related to elasticity. And in elasticity, my third quantity is also related to first and the second quantity, let me tell you. So when we talk stress, stress is observed in elastic body. And what is that stress? Sir, there is a internal, actually this is called internal elastic restoring force. The right definition is, it is internal elastic restoring force which will be act per unit area of the body. Internal elastic, we all have, my dear, we all possessing this force, that is because our body is elastic body. If you stretch a rubber, can you imagine that rubber when you leave it, how this rubber is come back to its original position? So when you stretch the rubber is under stress. So beautiful it is. When we stretch the rubber, any rubber band, you know rubber. So when we stretch any rubber, because rubber has a property of elasticity. Similarly, my skin has a property of elasticity. So if I stretch this skin, what will happen? The skin is under stress. The skin is under stress. The rubber is under stress as soon as I stretch the rubber. And therefore, my dear, the stress is giving a definition that it is an internal elastic restoring force. Why the word given restoring? Because as soon as I leave it, it will come back to its, it will restore. My skin will restore because of internal elastic restoring force. And this internal elastic restoring force will act per unit area of the body. Because of this force, the rubber or the any body which is deformed, after leaving the deforming force, after removing the deforming force, any elastic body is regaining its original shape because of this restoring force. And therefore, my dear, in shortcut, the formula will become, forget this internal, forget this elastic, forget this restoring. What is the quantity? Quantity is force divided by area. So the dimension of stress is nothing but dimension of force divided by dimension of area. Dimension of force is nothing but, my dear, in numerator I am writing L1 M1 T minus 2, and dimension of area is nothing but L2. So the entire dimension of stress will become, here it is 1, here it is L2. So 2 will go up, become L minus 1 M1 T minus 2. My dear, if you observe carefully, you will find that the stress has the same formula as pressure. Because pressure is also force upon area. And pressure is the same dimension as the dimension of stress. But my dear, stress and pressure are two different quantities. Don't tell that stress is only a pressure, because my dear, one big difference between stress and pressure is a scalar quantity and stress is a tensor quantity. Tensor. Scalar means they required magnitude only. You are knowing all this. Scalar quantity means only required magnitude. But that is your pressure. That is scalar. But stress is a tensor quantity. T-E-N-S-O-R. I writing this. T-E-N-S-O-R quantity. Tensor quantity. And tensor quantity, one is scalar, one is vector, and one more quantity, that is tensor. Tensor quantity don't need magnitude, neither need direction. Scalar need magnitude, not direction. Vector need magnitude and direction both. And tensor does not depend upon neither magnitude nor direction. So my dear, this stress is a tensor quantity. Though its formula is same as the pressure, its dimension is same as the pressure. Even SI unit of stress is nothing but Newton per meter square. That is same as the pressure. But you will not use the word Pascal in this, because Pascal is a name of scientist. I have discussed all this in my earlier video also. Pascal is a name of scientist which is used only for pressure, because he discovered the term atmospheric pressure. Okay, my dear. So I hope from my side you understood the concept of stress. So my dear, any rubber or any elastic body, they are regaining their original shape. You all know, sir, as soon as you will remove the force, right, the body will regain their original shape. On what condition? Because of what they regain their shape? Because there is an internal, in every elastic body, myself is elastic body, yourself is elastic body. In every elastic body there is internal elastic restoring force. And that internal elastic restoring force will act per unit area of our body and bring the body to its original position. So my dear, this is the case of stress, and this is the formula, force divided by area, because I am not interested in internal elastic restoring. It is just a concept I am giving. Ultimately quantity is force and quantity is area, so dimension will become L minus 1 m1 t minus 2. Now another quantity on the board is strain. Strain. My dear, strain is also a tensor quantity. It is also a tensor quantity. It also don't require magnitude, neither it required a direction. It is also a tensor quantity. Now, this quantity is also coming under a chapter of elasticity. Matlab stress and strain, this two word is from the chapter so called as elasticity. Whenever we read the chapter of elasticity, am I clear, my dear? You will have these two terms, two physical quantity, which are tensor physical quantity, and they are stress and strain. Now, my dear, what is strain? See, and let me tell you, stress and strain are so occurred together, For example, I am giving you, my dear, suppose I took a lot of bag on my head, and I am going somewhere to drop somewhere on the station. Suddenly I took a lot of weight on my head, lot of load I have took. Now that load can be called stress, because रबड़ को मैं जितना stretch करूँगा उतना internal elastic restoring force develop होगा. तो ultimately this concept is related to your load. Stress is a concept related to load. So जितना मैं load लूँगा, my dear, उतना strain body में आता है. That is muscle strain. You have used a word, sir, my muscles is got strain. Here you can see my finger. This finger is changed its shape, you can see, whereas this finger is straight. So I can say my left hand lady finger have got strain because this body is elastic body. So this finger has a strain. Now what is strain then? My dear, there is a change in dimension. Now when we talk about a body's dimension, there is three kind of dimension, as we are writing dimension here for physical quantity. So physical quantity are known by three dimension. They are length, mass, time. Right? There are many quantity also. Even current is used for dimension. Even luminous intensity is used for dimension. Even amount of substance is used for dimension, for physical quantity. But my dear, apart from that, when we consider elastic body, there is three things in elastic body which keep changing. One is length of elastic body is keep changing. You can take an example. My dear, when you are 5-year-old, you are too small, but when you become 10-year-old, your length of the body increases. It means there is a change in dimension of your body, and which part of dimension is changed? Length was changed. Suddenly, my dear, suppose I am a weak right now, I am looking slim, but after 5-10 years, you will find me little bulky, suppose. So what will happen? My size, my volume of the body increases. So again I will say, oh God, there is a change in dimension of my body with respect to volume. तो जब कोई fat हो जाता है तो we say there is a change in dimension of body with respect to size or volume. कोई छोटे से लंबा हो जाता है तो we say there is a change in dimension of the body with respect to length. And third dimension which is change in the body is with respect to shape. Now you can see, my dear, here my finger, lady finger shape is changed as compared to this finger. You can see. So try to understand that in elastic body there is three kind of a change can occur. Am I clear? Please make a note of this carefully. In any elastic body, the change can occur in three ways. Either the change occur in the length of the elastic body, I have given the example, हम बढ़ते चले जाते हैं. Either the change is occurred in terms of volume of the elastic body, that is size. Am I clear? And either the change is occurred with respect to shape of elastic body. Shape. Am I clear? Shape of elastic body. So my dear, these three things which I talk about, length, volume and shape, these are the dimension for elastic body. These are the dimensions for elastic body. Please take care. Elastic body में तीन dimensions हैं, length, volume and shape. Now my dear, if this dimensions, length, volume or shape, if they changes, then we say our body got strain. Our body possesses strain. Am I clear? So now my dear, here what is the definition of strain? Strain is change in dimension of a body, not dimension of physical quantity. Please understand, of a body to the divide by original dimension of the body. Of a body. So please don't get confused this dimension with the dimension of physical quantity. Here I am talking one single quantity strain which is related to elasticity. It is occurred in elastic body. In elastic body, sir, dimension is changed in three ways. Either it will be changed, I will write here, change in length of a body, change in volume of a body, and change in shape of a body. Now my dear, if it is change in length of a body, so that will be in numerator. That dimension where length is changed. But my dear, strain is what? Not only change in dimension, it is divided by original dimension also. So if the length is occurred with a change, if there is a change in length, then it will be divided by original length. And it is called as longitudinal strain. Matlab strain is also having three types. So normal strain, when we don't say any name in front of strain, it is change in dimension divided by original dimension. We don't know which dimension was changing. Am I clear? But when we give a word longitudinal strain, immediately you should say, oh God, dimension of body mein the length was changed. Then there the name was given longitudinal. There is another change in volume of a body per unit original volume of a body, and it is called volumetric strain. Volumetric strain. This is called volumetric strain. So nice. Sir, it is so simple. If volume is changing, it is volumetric strain. If length is changing, it is longitudinal strain. And if nothing is mentioned that what is changing, it is just strain. So here I hope you understood what is this. This is changing shape of body to the original shape of body. Original shape of body. And this is called, my dear, the third strain called shearing strain. Shearing strain with related to shape. So now, my dear, I am not interested with this right now because and believe me, this three quantity which I have written is related to this only. The longitudinal, the Young's modulus is related to longitudinal strain. Bulk modulus is related to volumetric strain, and moduli of rigidity, that is shear modulus, is related to shearing strain. No doubt, I am just trying to giving you the kind of a concept. This is not the actual definition of shearing strain, but I was writing this too, so I have written this also with the same manner, so that right now you just catch it out that what actually is happening in strain. But this is not the real definition of shearing strain. I just wanted to make a note of this, that what is happening in dimension of strain, what will happen. So now, my dear, here I said change in length. Change in length. My dear, the quantity is length. Divide by original length. What is the quantity? Length. So what will be the dimension? Length L power 1 upon L power 1. Oh God, so dimension will become L power 0. And mass is not there. So M power 0, even T power 0. So it means longitudinal strain is dimensionless. So dimension of longitudinal strain, what I got? I got the answer as L0, M0, T0. Because ऊपर भी length है, नीचे भी length है. Forget change, forget original. I am interested in quantity. Look at this one. What will be the dimension of volumetric strain? Volumetric strain. Sir, change in volume. मतलब in numerator it is L power 3. Divide by original volume, because dimension of volume is L power 3. I am not interested in change. I am interested in quantity. Quantity is volume. Am I clear? Try to understand. I am doing dimensions right now. So volume में change हुआ, divide by original volume. So नीचे भी quantity is volume. Numerator also the quantity is volume. So here it will be LQ divided by LQ. Again the answer will be nothing but, my dear, you can see L0, because cube divided by cube, L0, 3 minus 3. Mass है ही नहीं है, M0, T0. Oh God, volumetric strain is also dimensionless. So what, here also, shape of body divided by shape. My dear, in numerator the shape which I will take, in denominator the same shape I will consider. So again the dimension will be dimensionless here also. So here, this dimension L0, M0, T0 and this dimension L0, M0, T0 shows that they are dimensionless quantity. They are dimensionless quantity because, my dear, they are the ratio of same quantity. Here also length, here also length, here also volume, here also volume, here shape, here shape. Now, my dear, that's why I have written change in dimension of body to the original dimension of the body. It means, and dimension here, please don't get confused with this dimension. They are the dimension of physical quantity, whereas dimension of body is in terms of length, volume and shape. So ultimately, what will be the dimension for strain? Sir, it is L0, M0, T0 because why it is dimensionless? Because it is ratio of two same quantities. Because it is ratio of two same quantities. So I hope you understood the dimension of stress and dimension of strain. That, my dear, that stress and strain, stress possesses the dimension as the same as the pressure, but strain don't have a dimension because, sir, it is the ratio of two same quantity, and its definition is change in dimension of a body to the original dimension of a body. Dimension of a body is in three sense: length, volume and shape. So if there is change in length, in denominator there will be original length. So ultimately it will be the ratio of two same quantity, length, and it becomes dimensionless. If there is change in volume, because I said dimension of body is length, volume and shape. So if there is change in volume, in denominator there is original volume. So again it will be volume divided by volume. That is dimensions के term में LQ divided by LQ. Answer will be L0, M0, T0. Again it is dimensionless. So in every steps, that strain quantity is dimensionless because it was, according to definition of the strain, it is the ratio of same quantity. So my dear, I have explained you this two quantity which is very important to do the rest part of the chapter. So please make a note of this. Then I will go for the third one, that is elasticity constant, which is related to stress and the strain. And therefore I took these two first, and then on third I have written elasticity constants.